Welcome one, welcome all, I am back, and today I have something a little bit different for you, something I am calling the coolest mathematical sequence ever. I know originally I said I was just going to be doing gaming and music, but I recently discovered this and I thought, you know what, I have to make a video about this. So I threw together a PowerPoint and hopefully it's enjoyable. So this starts out pretty simply with a square. Around that square there's going to be another square. We can say that the side of the smaller square is x, and that the distance between the side of the smaller square and the side of the larger square is y. Therefore, the side of the larger square is going to be x plus 2y. Now, the question is simple. What values of x and y will lead to an area A of the smaller square that is 1 greater than the area remaining in the bigger square? Well, this boils down to some basic math, namely this equation here. Now that may look complicated, but in reality it's just the outer square minus the inner square equal to the inner square minus 1. Basically, the remaining area in the big square is equal to the area in the little square minus 1. The left side can be simplified to give us this equation here, 4y squared plus 4xy equals x squared minus 1, but any attempts at further simplification would just be moving around the variables. So if we graph this, we get something that looks a little bit like this. This here is a hyperbola, but as you can see there are quite a lot of answers here, so we're going to try to narrow our search down to just the whole numbers. That's all the numbers in this quadrant that are perfect multiples of 1, starting with 0. The first solution is quite simple, 1, 0. You start out with a square with sides 1, giving you a total area of 1. The next square, with 0 added to each one, gives you another square with sides of 1, right around the outside of it. The area of that square, 1, minus the area of the square inside of it, 1, leaves us with 0, and the area of the blue square, 1, minus the remaining area, 0, gives us 1. And that equals 1 right there is what we're looking for. Now if we look back at the graph, you can see that the next solution is right here at 5, 1. 5, 1 works the same way, and as you can see, it ends up with an equals 1. I've done the math for the next two that work here, and these are only the solutions that have whole numbers for the x and y coordinates. As you can see, both of these end up with equals 1 as well. So now we've got 4 different coordinates, and with this we can start to see a pattern. As you can see, the 1 and the 0 add together to form a 1. This happens with the next two as well. So without even looking at the graph, we can say that the next solution for this question, such that both the x and y values are going to be whole numbers, will have a y value of 204. You can also think of this as the addition of all the previous x values leading to the next y value. The question still remains though, what is this number here? The x value. Well, to do that, we're going to need to get rid of a few extra numbers and focus only on the x pattern. Now for those of you who are mathematicians, you might recognize this pattern. It revolves around 2n squared minus 1, resulting in a whole number square. This pattern has the lovely name of A001653 according to the online Encyclopedia of Integer Sequences. You can see that all 4 of the numbers we have result in a different number squared. The numbers going across the bottom of the screen are the numbers that work in this pattern, and you can see they get really big really fast. It's kind of scary to think that in the first 300 million x values that are whole numbers, only 20 of them actually will result in y values that are whole numbers. I'm just going to let these scroll across until the very end. So you can get a nice good look at that huge 5 quadrillion number right there. So now we're going to take a look at the y values. These here, 0, 1, 6, 35, and 204, also form a pattern, with their squares resulting in triangular numbers. Now a triangular number is a number that is formed like these pictures here. 0, 1, 36, 1225, and 41,616 are all triangular numbers, and they're all perfect squares of these numbers here. These are the square roots of the perfect square triangular numbers. This is sequence A001109 in the online Encyclopedia of Integer Sequences. So it's amazing to think that with just a simple question of x and y values producing whole numbers in this square pattern, we get, for the pattern x1, y1, x2, y2, that any y value is the sum of the previous x and y values. Any y value is also the sum of all the previous x values. 2 times any x value squared minus 1 produces a prime n number, and the square root of any y number will be a triangular number. And that is why this is the coolest mathematical sequence ever.